Okay, so first of all, I want to make it very clear. I do not want you to change the assignment that you're turning in later in the week regarding the air pressure and depth of warm water in the Pacific. But it has everything to do with today's topic, and it's an important topic in terms of global environment because it is related to a thing known as INSO, or the El Nino Southern Oscillation. And this changes the weather patterns, the distribution of water all over the planet. And it's just an important atmospheric phenomena that is global in scale, and it affects ecosystems all over the planet. So let's get on. So El Nino refers to a phenomenon that occurs every, say, 2 to 7 years, in which warm water migrates across the Pacific, from the Western Pacific to the Eastern Pacific. So this red it represents warm water. Normally, the water is cold over here in the Americas, at least in the Pacific parts of the Americas, but this warm water arrives. And when it does, it changes weather patterns because warm water causes convection. So normally, you don't have a lot of convection here. You normally have it over here. And so that changes not just weather in the Americas, it changes weather on the entire planet. And it's something that it changes, it causes flooding, it causes drought, it causes forest fires, it causes all kinds of changes in fishing results. So it's just a really important thing to understand, and we still don't quite get it. I mean, we can recognize it when it's happening. That data you were looking at, it came from the NOAA, the National Oceanographic and Atmospheric Association of America's website that was specifically looking at indicators of the onset and the termination of these INSO events. Now, the word El Nino, it comes from the Peruvians. Basically, it means, those who take Spanish, it means, I think it's either little boy or little baby boy or something like that. But basically, it got this name because the fishermen in Peru, for hundreds of years, maybe for thousands of years, they had great fishing most of the time. It's one of the most productive pieces of ocean anywhere. The fishing is so good there. The people are just fat and happy. But every 2 to 7 years, things get messed up. This fog rolls in, the fish go away, everybody goes hungry. And these conditions with warm water and fog and no fish, it often would first happen around Christmas time and then last through almost a year. And so because it started around Christmas time, the local people who first noticed it in Peru called it El Nino. But here's the thing. So I'm going to simplify this a little bit. This is a lot more complicated, but let's just simplify. Let's just say, okay, here's the west coast of America. We're near the equatorial Pacific, so trade winds are blowing this way. As the trade winds blow this way, they drag this water here away from the shore. Well, something's got to take its place. Where's the water going to come from? Down below. Well, I have to remember, when organisms near in the photic zone, where all the light is, all the plankton up here, then there's the phytoplankton, the zooplankton, the fish that live up here. When they die, they sink down to where there's no more light anymore, and not much oxygen anymore. And in that low oxygen environment, it's hard for them to decompose, and they break apart. But the bottom line is, there's an awful lot of nutrients that settle to those dark, deep waters in the ocean and just sit there forever, right? But what happens is, as this wind blows this way, it drags the surface of water away, and that cold water comes up from below to the surface. So they normally have very cold water here, but it's very rich in nutrients. And when those rich nutrients come up to the photic zone, and now there's light, well, guess what? Now all that phytoplankton has all these nutrients to build cells with. So there's this explosion of phytoplankton, which makes an explosion of zooplankton, which makes an explosion of fish, which makes the fishermen really happy, which makes the birds really happy, which makes the whales really happy. And you end up with this patch of ocean that's just super, super, super productive until El Nino happens. And then there's no more upwelling. So all the productivity stops. The fish migrate away, and the whales swim away, but the people don't, and the people go hungry and they get upset. Okay, and that's called El Nino. So in normal years, what happens is trade winds, if you recall, blow from east to west across the Pacific, and as they move across the equatorial Pacific, they drag. I should go the other way on this. They drag warm water with them. And so this water gets dragged across the surface of the ocean. But when it gets to the Western Pacific, there's a barrier. You've got Australia, you've got the Indonesian archipelago, you got the Philippine archipelago, you got the Asian mainland, and so this water, it can't keep going westward anymore. So it piles up here, forming what's called the West Pacific Warm Pool, which you guys were looking at in your data. So let's take a look at it here. So the West Pacific warm pool happens over here in the West Pacific. So let's just say this is Asia, this is America, okay? And what we find is that the warm water is going to extend much lower over here. In fact, on the shore here, the cold water comes all the way up. And so because the warm water is being dragged over this way, it gets deeper here. And so we get this pool of warm water over here in the West Pacific near Darwin, Australia, and the Philippines. And not only that, these winds, as they blow, they hold the water higher on this side. So as weird as this might sound, the sea level off the Asian coast tends to be about half a meter higher than it is off the Americas coast, at least in these equatorial regions where you have trade winds. And it may not seem like a lot, but if you multiply that out over all this area, what you find is that there's a tremendous amount of warm water here. I mean, half a meter of ocean water covering all this area is a lot. And so there's this big pool of warm, high energy water sitting over here off Australia and Asia. Well, what does that warm water do? One thing it does is it causes convection. So we end up getting a lot of convection in the Western Pacific over this warm pool. We have, and it's water, so it's got a lot of evaporative water vapor with it, which as it goes up, it precipitates. So we get a lot. This is a big factor in driving the Asian monsoons. So the monsoons that Asia enjoys that help them with their agriculture are largely attributed to this pool of warm water that occurs here. And then the seasonal variability just has to do with the tilt of the Earth. We'll talk about that later in the year. But it establishes this east-west convection cell. Remember, we have the Hadley cell, which raises at the equator and drops at 30 degrees. But now there's this other one that gets established that rises in the West Pacific and sinks in the East Pacific. All right, so there's like sort of a double convection happening here. All right, now we already said this about the rainy weather here. Okay, now this convection cell, which is known as the Walker cell, one thing it does is it causes a strength in the trade winds because the Hadley cell, because of the Coriolis effect, makes trade winds even without this warm water here. Like you don't have this warm water to this extent in the Atlantic Ocean, but you still have trade winds. But here what you get is very, very strong trade winds because they are enhanced by and reinforced by this Walker circulation. So the trade winds in the Pacific tend to be really, really strong. That's why they're able to hold the water half a meter higher over there. All right, now this phenomenon is an excellent example of something we'll talk about several times here, which is known as a positive feedback loop. So let's just dive into what a positive feedback loop is. So a positive feedback loop is basically anytime there's a situation in nature in which the outcome of an action causes an increase in either the rate at which an action happens or the magnitude at which that happens. So take a fire, okay? I have a forest fire. So I have a small piece of wood gets hot. But when it gets hot, it causes the temperature to go up around it, which causes more flames to occur. Well, that causes convection, which brings in more oxygen, which causes the fire to grow faster, which brings in more air and more heat. That's a positive feedback loop. So a forest fire is a good example of that. Well, this is a good example of it. Another good example is cherry blossoms. It's weird how they all seem to happen at the same time. Well, what happens is when a cherry blossom blooms, it releases a chemical. That chemical causes other cherry blossoms to bloom. So then more open, making more chemicals, which makes more of them bloom. That's why all of a sudden you'll go from having cherry blossoms about to go to all of them going at once. It's because there was this positive feedback loop. Well, we get that in the case of the Pacific warm pool. So let's see exactly what happens here. Okay, so we have warm water causes convection. Convection causes a strengthening of the trade winds. Strengthening of the trade winds moves more warm water over here, which causes stronger convection, which causes more water to be dragged across, which causes more warm water to pool up, which causes more convection, and so on. That's what we call a positive feedback loop. The outcome causes a greater amount of the outcome, or at least, or some cases, a higher rate. Okay. Now, for reasons that we still don't know, every 2 to 7 years, something happens that breaks this feedback loop, and we call it the Southern Oscillation. There's this sudden shift of air pressure between Darwin, which is pretty much a good place to measure the Pacific warm pool, and Tahiti, which is in the mid-Pacific. So under normal conditions, when this Walker cell is well established, what we get is warm water here, low pressure, lots of rain here, and then the Walker cell goes across here. But we find the pressures tend to be lower here off Tahiti, higher here off Tahiti than they are off Darwin, where we have all this rising warm. So once again, low pressure, high pressure, normal conditions, strong trade winds, building up this pool of warm water, positive feedback loop. But then there's this shift in pressure that happens, and all of a sudden, for a reason we don't know, that low pressure shifts over here to Tahiti, and higher pressure comes into Darwin. And what that does is this breaks that Walker cell. And so when I have low pressure here, that means I'm going to have convection happening here instead. And so what happens is this low pressure cell moves across. So when that happens is we get a smaller cell, we get weaker trade winds. The warm water tends to follow it because now we have westerly winds where we normally have trade winds. And so now the wind is blowing in the opposite direction, pushing this warm water across as it goes. That causes this thermocline. Because this is weak, it causes a termination of the upwelling, and this blob of warm water will eventually make its way all the way across the Pacific Ocean, triggering what we know as El Nino. And Tahiti is right about here. So we notice this drop in pressure during these El Nino events. Now, what does that do? It changes the whole world's weather. So now we have dry winds here. We don't get the normal monsoons. We have drought conditions. We have forest fires happening in Australia and Asia. The cattle are dying from lack of food to eat. What happens is over here we tend to get more rain, and as this warm water moves across, now we're getting floods in the deserts of Peru. We're getting lack of snow happening in parts of America. We're getting droughts in parts of Africa. It just changes the entire weather pattern of the entire planet. It's in a way kind of catastrophic because nature relies on consistency, and this represents a total lack of that. Now, the main thing that happens here, though, is the movement of warm water. So remember, normally the trade winds, could be courtesy of the Walker cell, are forcing water over here to make this warm pool. And remember, the water here, it's like a half a meter higher. Well, you take away this trade wind, you weaken this these trade winds by moving the low pressure from here to here. And now what happens is you get winds that are blowing this way. And all this warm water that piled up here is going to move back across the ocean. And now, where I normally have all this warm water off of South America, we now have all this warm water. Now we're going to get all this rain happening over here. And it ends up causing changes in Australia, the Americas, Asia, everywhere. Africa, the whole world has a demonstrable change in its weather as a consequence of the movement of warm water and the subsequent convection that goes along with it. And convection drives wind patterns, and that changes everything. So here's a good example of under normal conditions and under El Nino conditions. And all has to do with, if I have low pressure here, I have this positive feedback loop that keeps the warm water over here. When that breaks during an INSO event, now the low pressure moves to here. So now I've got winds blowing this way, forcing the warm water back across and screwing up the weather for the whole world. So here's just another graphic to try to show you. So normally we have the warm water. Here's the warm pool under normal conditions. Here's Tahiti out about here. So we get this Walker circulation pattern. But in El Nino conditions, now I have this moves out to where Tahiti is. And now I have water winds at the surface of the Pacific blowing in the opposite direction that the trade winds normally would. So a weakening or even reversal of the trade winds as a result of the change in the position of this Walker cell. I'm going to skip this one because it's just showing like where you get weird weather, right? So if you look at this, you get warmer winters here. You get droughts in certain places. You get floods in other places. So effects of an El Nino is you get a weakening of the Asian monsoon, You know what? It didn't end up in this, but one of the main things is off the coast of Peru, there is a total uh, crash of the fish population, and the fish population that don't die of starvation just migrate to other places. So during an El Nino, you'll get fish from the tropics showing up in Alaska. You get drought conditions in southern Africa. You get all kinds of rainfall in Africa, the U.S., Argentina, places that normally wouldn't, they're normally fairly dry, are suddenly getting flooded. Now, there's this thing called La Nina you might have heard of. So La Nina it's not really like a native term like El Nino. It's one that people just coined, but it's basically the opposite of El Nino. Again, for reasons that we don't know, sometimes this Walker cell over the warm pool just revs up more than normal, and we get a deepening of the warm pool and an even stronger Walker cell circulation, which forces more warm water across and even drags cold water across. In which case, again, this is going to change weather patterns across the world. So La Nina tends to be a little bit less catastrophic. Basically, what happens when we get this is we get very dry conditions here, and we get very, very wet monsoons. We tend to get flooding. So when you hear about like floods that happened in Australia, it was during a La Nina event. So under La Nina, we expect to have more rainfall associated with the Asian monsoon, flooding in Australia, Africa and Brazil get a lot, but then it gets drier in the southern United States, more forest fires, it's drier in Peru and places like that. Okay, so sorry this is a bit of a long one, but well, see ya.